Alrighty, guys. Can you hear me again? Can you guys hear me?
Yes.
All right. Let's so that was one loose end, and the other loose end that we have is the American call. You have seen some of these arguments given in the TA session. So now I'm going to give a similar argument here for the American call. But we have been working exclusively with puts in these lectures, and the reason for that is the following result. Like so we're going to turn our attention to the American call. So this is where G of Sn is, you flip it, so it becomes Sn minus K at a positive part. And right, so the claim, the theorem, if you want, the theorem is that if the interest rate is positive, then the American call is equal to the European. Right, so the American call, this is the supremum over tau taking values, say, between 0, 1, up to some finite time n of E 1 over E tilde 1 over 1 plus R of S tau minus K positive part. That's the European one, and then that's the American one, and then the European one is just the expectation of 1 over 1 plus R, and then there's an N here instead. And then we have Sn minus K positive part. Right, so the proof goes, what we're going to be doing is we're going to be proving that the optimal stopping time is just going to be to wait until the end. And so the way that we do that is to claim that if I look at Sn minus K divided by 1 plus R to the nth, this object here, this is a sub-martingale. Right? Sub-martingales are the ones that have a tendency to increase over time. Okay, so let's prove the claim. We're going to be looking at an expectation of Sn plus 1 minus K positive part divided by 1 plus R n plus 1. Okay. So we can for sure put the interest rate component, we can put him outside. So this will be 1 over 1 plus R n plus 1. And then what can we try to do? Well, we can use, if I look at the map that maps X into X minus K positive part. Right, this is my hockey stick that looks like this. And this one here is going to be convex. So what comes to mind is that I have a convex function. So I can use Jensen's inequality. Use Jensen's inequality. So now this equality sign is going to be replaced by a bigger than, less than, equal. We have to think about which way it should go, but let me do it first. So that means that the plus thing is going to go outside. So I have an expectation. And then Sn plus 1 minus k. And then the plus goes outside. And so what's biggest? Is it biggest when the plus is inside, or is it bigger when it's outside? Excuse me. Which one is biggest, the left-hand side or the right-hand side? Let's try that again. Is it bigger when you have the plus inside, or is it bigger when you have the plus outside? Okay, so it's biggest when you're inside, that's correct. So we're going to do this one. And then what? So then we write that this is equal to, so here we have the discounted stock price. I know that's a martingale, so we'll get here Sn divided by 1 plus r to the nth, and then minus, and then you have a k here, k divided by 1 plus r to the n plus 1. Positive r. So we're almost there now, but it's not quite. We want this 1 plus r, let's put that outside. We have 1 plus r outside. Inside I have Sn. I have minus a k, and then I have 1 plus r here. So now we need to think about, what it is I want it to become. I would like to get rid of this. I want to prove that this is a sub-martingale, so I'm almost there. I just need to get rid of this term. I just need to get rid of this term that I have down here, then the claim is proved. So how would I do that? Well, I'll have that r is positive. So k is bigger than k over 1 plus r. So this implies that k is bigger than k divided by 1 plus r. So then if I take an x and I subtract away k, then this is going to be less than, it's going to be less than x minus k divided by 1 plus r. Because over here I subtract away less. Okay, and then I have a non-decreasing function. So that's going to imply, so this implies that, and then I'll take positive parts on both sides. Now that's at x minus k, positive part is going to be less than x minus k divided by 1 plus r, positive part. So now I get a bound. Instead of that, I could write here 1 over 1 plus r to the nth, and then I would have Sn minus k positive part. And that's because of the calculation I have on the next slide. So we used to get rid of this 1 plus r here, I used that r is positive. Okay, so then, so if I have a sub-martingale, then in particular, in particular submartingales that you have increasing expectations. So you wait as long as possible. So there are lots of these examples in the problem sheets. If you can prove something is a submartingale, then you hold on to it for as long as possible. Any questions on this one? So then you could, for example, you could look at the perpetual call. You can look at the perpetual call. So you have the supremum tau stopping time. And let's take tau omega to be between 0, 1, 2, and so on. And then I'll have E of 1 over 1 plus R to the power tau. And then you have S tau minus K, positive part. Right, so here I'm not allowing tau to be plus infinity. So we're not allowing tau omega to be plus infinity. Right, because then I have to give meaning. I have to give meaning to S at infinity, and I don't have necessarily anything to put in there. So knowing that you should wait for as long as possible, in a finite horizon case, what would be a natural conjecture here for the perpetual one? Right. This is the finite time horizon one because we have an n up here, and there you wait for as long as possible. So now here we have a perpetual one, we have an infinite horizon one. There's no n here. What would be your guess on what this should be? What would we guess that the value function is, and what would we guess that an optimal exercise time would be? Any guesses? Right, so we were at this point here. Last time when we were doing the put, right? And then we have to come up. Like, so what is V of S0 equal to? What is an optimal time? Right, we were at exactly this point here last Tuesday when we started analyzing the PUD, and so what would you guys think? Like, what is the value function? I mean, it's by definition equal to this stuff, right? But before we had this nice formula, it was like, what was it, 4 minus x when x was small, and then it was 4 over x when x was big. What about here? What could it be? Nobody wants to make a guess? So we just try to get you guys started. How would we do it? Well, how did we do it last time? When we start looking at a picture, And so here's my k, and so it runs up like that. So this here is x minus k positive power, right? So that's my hockey stick. And we're looking at an equation like the one before. So this was v of x would have to be, well, we can exercise. If we exercise, we're going to get that one. This would be x minus k positive part, or we could continue. So this will be our 1 over 1.25, 1 over a half, and then we'll have our v of 2x plus v of x over 2. And we take the max. So we need some solutions to this form here. And so what we're looking for is we're looking for stuff such that I need my v of Sn. I need this thing to dominate. I need this thing to dominate Sn minus k plus. I also need that v of Sn divided by 1 plus r to the nth. I need this to dominate. I need this to be anybody? What do I need it to be? Well, that one we should have, right? There are a bunch of properties that the value function should satisfy. It should satisfy that it dominates the obstacle, right? So it has to be bigger than this thing. It has to be such that when I discount it, I should get a what property should this stochastic process here have? No, it should not be a martingale. It should be a it shouldn't be a martingale, it should be a oh no, Marco, no, come on. Oh, we just did this, guys. It should dominate, and it should be a super martingale. So it should be a super martingale. What's the third property it should have? Well, what did we prove with the put? It should be it should dominate the obstacle. It should be a super martingale, and it should be should have this property that it should be the smallest such process. It should have this minimality property. So it should be a dominate the obstacle, be a super martingale, and two, it should be that V of Sn is the smallest such process. And if you were to describe an optimal exercise time, so an optimal stopping time would be when V of Sn, what should it become equal to? Or what did V of Sn become equal to before? Or what was it before? In the example before, the optimal exercise time is the first time when you take the stock price, you plug the stock price into the value function, and the value function becomes equal to the obstacle. I think Sherry was asking about this at some point. Yeah, it's this stuff here. Like, so when it's tau star is the first time that, yeah, so here it is, right? So tau star is the first time that your V becomes equal to the hockey stick. So we guess, presumably we will make that same assumption over here. This is the first time that this becomes equal to K minus Sn. The first time that the value function, this is the thing that we're trying to figure out what is the first time that it becomes equal to the hockey stick. Any guesses on what we could choose for our V? I need something, and this is the equation I have to start out with. So what could I pick here? I need something that is bigger than Sn. I need something such that when I discount it, I get a super martingale. What's our favorite discounted process that has a martingale property? Do we have any favorite processes that has this martingale property? What would happen here if I would just put X? So would I have, well, I would obviously have that X is bigger than X minus K. So could it be that this is equal to X? And then that would hold. This will be Sn discounted, right? So that would be a martingale. In particular, it will be a super martingale. And then there's a question about, so this is okay, this is okay. This one here is a question, we don't know that. And an optimal stopping time would be the first time when Sn satisfies that these two become the same. But X is never going to become equal to X minus K. So if this is true, then there is no there's no optimizer. This is because X is strictly bigger than X minus K plus the power. So is this this minimality? Is that in there somewhere? You guys are very quiet. Is this hard to follow?
I think it's okay. It was just I realized I was confused previously because it was a put. Like, so I kind of just got the concept of tau kind of like mixed up, but I think it's clear now.
Right, so before we were looking at this picture here, right? So we had the value function. The value function is the curve. This is this 4 minus x divided by 4. This is our guess for what the value function is. And so when do we exercise? Well, we exercise when the stock price dips below, it dips sufficiently far, right? So that means when the value function becomes equal to the hockey stick, right? And so we just read off what it is, and that's 2. So we would presumably we would use that knowledge to carry over and say, like, well, what about over here? Would this, if you are to believe that what we were looking at before is just an example of the general theory, then we would imagine that when should we optimally exercise? When should we optimally exercise the call? Well, we should optimally exercise the call the first time that the value function becomes equal to this thing that it always dominates. So if you have a good idea about what v should be, so here I'm throwing out, just take v of x to be x. Then if that's the case, right, v never becomes equal to, it's always strictly dominating the hockey stick. And also back to this discussion that we could decompose a super martingale into 2 parts. So we could write it equal to a martingale minus something increasing. But here, if v of x is equal to x, then you would have that this is a martingale, and it's then finite variation. This is an increasing process that you would have over here. This would be constantly equal to 0. And so the first stopping time would be the first time that it becomes non-zero, but that never happens. So again, there is no optimal time. So what remains to be proven here is that this v that we're looking at, this guy up here, this indeed is the smallest one. So how would one go about maybe trying to justify something like this? So I don't want to take you through all the calculations one more time, but just where would something like this come from? Like why would it be that the stock, why would it be that the stock is just the price of this perpetual American coal is just going to be the current stock price? Well, so it's maybe just to get some intuition for this. So if I choose, okay, so set. So what is the claim? The claim is that the first one is that Sn is really dominating Sn minus k positive part. And the second one is that Sn divided by 1 plus r to the nth, this is a martingale in particular, a super martingale. And the third one is it's the minimal such process. Just to get some headway on this, so we from these two properties, we do get that we do get if I would take so as before, we will consider like tau valued in n plus 1 and so on. We'll consider an m bigger than n, and then we will look at the conditional expectation of 1 over 1 plus r tau min m, and then we would have S tau min m minus k positive part. So we will use that if I put S here instead of this difference, I'm going to get something that's bigger. Right? So I'm moving up on the dotted line. So this thing here becomes less than E tilde n 1 over 1 plus R tau min m. And then here we'll have S tau min m. And then I'll do optional sampling as we did before. Like this here is a martingale evaluated at the stopping time. So this here will be the same as 1 over 1 plus r tau min n S tau min n. And then I'll use that n is smaller than or equal to tau. So this here will give me 1 over 1 plus r n Sn. This is very, very similar to what we had before. So now what we'll do is we'll pass m to infinity. So we have to be more careful here. We'll pass m to infinity, take the supremum and so on. So this would give us, so this here will imply that if I take the supremum over tau of say E tilde 1 over 1 plus r to the tau S tau minus k positive part, right? And this would be less than S0. So we get one bound, right? And so before what we had was we also had an upper bound, and then we got the upper bound was to use a martingale property. So if I choose, so if we could choose tau just to be n. So in that case, I'll have that the supremum over tau E tilde 1 over 1 plus r is tau minus k positive part. Right, so now I'm taking a specific stopping time, and so I'm going to get a bound. This supremum is going to be bigger than if I just look at that particular stopping time up here. I can pull it out. So we're basically just redoing this Jensen's inequality argument we had from before. If I pull out the plus, so it comes outside, I'll have E tilde. I'll have E tilde, and then I'll have Sn divided, no, the division is already outside, minus K. And then I'll have positive bound. And so what does that become? Well, let me have a look, right? So there will be two components inside here, right? I'll have E tilde, I'll have Sn divided by 1 plus R to the nth, and then I'll have minus K divided by 1 plus R to the nth, and then I'll have a positive bound. So what happens with these two terms here? Now pass n to infinity, because there's no n on the left-hand side. So pass n to infinity to get what? To get the supremum over tau E tilde 1 over 1 plus R to the tau is tau minus K positive part. This is going to become bigger than, and now I'll pass this to infinity. There are two terms. Where does the first term go? Where does that term go? What is the expectation of Sn divided by 1 plus R to the n under the risk neutral measure? What is this quantity here? The super martingale property, but in this particular case here, Sn divided by 1 plus R to the nth, this is not just a super martingale, it is a what is it? It's not just a super martingale, it's a discounted stock prices under the risk neutral measure are okay. So if I would go, what would happen if I would do n here, say n minus 1, Sn divided by 1 plus r to the n. What would that be equal to? Yeah. And so what do you get in the end? This is equal to Sn minus 1 divided by 1 plus r to the n minus 1. Right? Discounted stock prices are martingales. So what is this thing here equal to? Oh, still no? Okay, so let's go back one more. En minus 2. So we have En minus 2. What is this one? Well, it will be a martingale. So this will be equal to Sn minus 2 divided by 1 plus r to the n minus 2. And then you keep going. What do you end up with here? Well, she says it's going to be there's no conditioning here, right? There's no conditioning here. This is just an expectation. What is the expectation of a martingale? Yes, thank you, Mio. This is S0. And what about this one? This is a constant. So we're going to have here, pass the limit to infinity. So I'm going to have a limit here of n going to infinity. And then I'll have S0 minus k divided by 1 plus r to the n. And what is that equal to? Well, this is where we're going to use that r is positive. So I'll have S0. And where will this guy go? K divided by something that is strictly bigger than 1 to the power n. As n goes to infinity, this term here is going to vanish. I'll take the positive part of S0. I'm just going to get S0. So then we can combine. We can combine the two expressions. So on one hand, the supremum here is less than S0, and on the other hand, the supremum here is bigger than S0. So this shows that V of S0 is S0, and there is no optimal exercise time, because the function, these two did never coincide, right? So I cannot find any time such that when I plug that stopping time into V, I'm going to get the same thing as when I take the stock price at that stopping time, plug it into V, I'm going to get the same thing as when I plug it into the hockey stick. This is always above this one. So that's the call option. I know some of you have mentioned this thing about the supremum. Why is it we have to write a supremum? Why is it we cannot just have a why is it we cannot just write a max here? This has been mentioned in both, this has been mentioned in the office hours, right? And so the reason that we cannot write a max is, for example, illustrated here with the call, because the supremum here, there is no stopping time in this set. There is no stopping time in this set that will give you S0 on the left-hand side. This is supremum here is not attained. This is not a maximum. So the answer here is what is an optimal stopping time, so that there are none. There are no such times. And this one here, this is S0. Are there any questions about all the stuff that we've been talking about today? We tied up some loose ends related to American options. Are there any questions about what we've been doing? Any questions or comments about what we've been working with? If not, maybe we should have a quick look in our textbook. So this is the first textbook. So what have we been talking about the last few times? We have been talking about chapter 4. We have not touched upon section 4.4 very much. These general ones, this is when you can have path dependency. Our intrinsic value processes have just been a value, just been a function of the current stock price. This is more general. We spent, today we cleaned up a loose end. So we did this American call option, finite horizon American call options, and showed that the reason that call options are not really discussed in these sections is because they are the same as the European ones. And then we moved into section 5 here. We talked about we've talked quite a bit about first passage times, both last time and the time before then. We did not do section 3.3, so reflections. We have not talked about that. We have spent a lot of time on the infinite horizon American put option. Over in the exercises, you will find the perpetual American call that we just did. This is exercise 5.8. The calculation we actually just did was this one we had down here, that the first part here is coming from a martingale structure. This is what Wang was writing. That is 0. That's in the chat. This is exactly that is 0 sitting here. Then you had k over 1 plus r to the power n. You pass n to infinity. You're going to get, that term is going to go about. So we did this exercise too, and then that would be the end of what we'll be talking about in chapter 4 and 5, right? So we did not do 4.4, and we did not do 5.3, but we have done all the other ones. We've done some of the exercises and so on. Are there any questions on this part of the course? If not, we're going to move on, and the last section in the textbook is chapter 6. So this is what will be referred to as a fixed income. Fixed income. And the focus now is, going to be on interest rates. So up until this point, we looked at equity models, and equity models typically take the interest rate to be constant. Now we're going to move into the fixed income portion of the course, and there the interest rate is not going to be constant. Okay, so make sure we get the number right. 16, so we're at 17. We're going to do fixed income. I mean, fixed income. This is a very large part of fixed income. We also call it derivatives. I mean, fixed income derivatives. This is a very large part of quantitative finance. Let me just. So for us, this is section. This is section 6. I listed some textbooks. Fixed income is a huge, if you are to go into quantitative finance, which most of you will, I mean, fixed income, this covers just a very, very large chunk of any portfolio. Right? So on the syllabus, I just want, for those of you that will end up working with fixed income, it will be probably quite important to master more material than just what we're covering here. So in the syllabus, I listed a book on fixed income. Some of you might need this. And it's this book here, Fixed Income Modeling, 2011. This is an entire book that is just devoted to fixed income analysis. So if you go to fixed income analysis, there are many of them, but this one here is a good one. And if you look at table of contents, you can see like there's 16 chapters written on just fixed income, right? So we're looking at a book that's 500 pages long. So this is, I'm trying to give you the impression that this is a pretty large area of quantitative finance. There's a tendency to focus a lot on equity derivatives, so American and European options written on the stock, and that's fine, but one should not underestimate the practical relevance of fixed income derivatives. Okay, so what are the differences? So in equity models, you will have your money market account will have the property that it's just given as 1 over 1 plus r to the nth. Like for a constant r, which is typically bigger than -1, or r is positive, as we just used. So the typical assumption is that you will have a constant interest rate in equity models. If you move into fixed income, this is going to change. And the way that it's going to change is that SN0 is going to be given by, it will be the previous one, as we used to, times, and then you have 1 plus, and then it's going to be written now with a capital R. This is what the textbook does, n minus 1. And very often we'll start out just being 1 at time 0. So fixed income models, this is the starting point. And so here, this is a stochastic interest. And you should still compare with stock dynamics. Like there you have your SN would be again the previous one, and then you would multiply onto your psi. So you can see that there's a difference in indices. Here it's n minus 1, and here it's n. Right. So keep an eye on this one and keep an eye on this one. So Rn minus 1 is Fn minus 1 measurable. This is going to imply that Sn 0 is also Fn minus 1 measurable. This thing here is not like that. This is not Fn minus 1 measurable, but only Fn measurable. So that's a big difference, even though the structure looks very similar. The interest rate that you're working with in these fixed income models, they are stochastic, but they are not as wild as the stock price dynamics are. So for example, if you look at just in a 2-period case, for example, if you would look at Sn, so let's call it Sn1. Right, so Sn1 would be the initial value, and then it will be 1 plus R0. And so S2, this is going to be 1 plus R0 times 1 plus R1. So what we see here is that, so this one here, this is F0 measurable. This one here is F1 measurable, but not F0 measurable. So contrast this with the stock. If I were to write down the stock at time 1, this would be the initial stock times the first coin flip. S2 would be the previous stock price, so S0 times psi 1, and then times the next coin flip. And this thing here is F1 measurable, and this one here is F2 measurable, and this one here is not F0 measurable, and this one here is not F1. So the interest rate somehow is random, but it is, you know what the interest rate is over the period at the beginning of the period. And you don't know that for the stock. So we're going to be talking a lot about bonds. So in fixed income, zero coupon bonds, so do you call ZCB, they are the basic starting point. So let's see what a zero coupon bond looks like. So the payoff, so this year's time, we're looking at we're looking at an M. And out here, if it's a zero coupon bond, here in the future, you're going to get $1. And then you're sitting over here time N. This is current time. This is expiry. Right, and this is time 0. So a zero coupon bond, what you need to do is you need to move this payoff of $1 here, and then you've got to move it over here. So let's return to these two examples, just a 1 period and a 2 period model. If I'm interested, and so what you're denoted by is like B, N, N. That's my stochastic process. It runs from N equal to 0 up to M. Those are my zero coupon bond prices. And so if I am to look at a zero coupon bond, say in just in a 1 and a 2 period model. So if I'm looking at B, say 0, 1, and B, 1, 1. So here I'm having M equal to 1. How much am I willing to pay? How much am I willing to pay today to get $1 at the end of the next period if the interest rate is R0? And what is this one equal to? How much am I willing to pay today to get $1 today? So there are two questions. Does anybody know what these two are in the model up here? We should start with the second one. What is the value of the zero coupon bond if it expires immediately? What's the value? B11. How much are you willing to pay to get $1 immediately? Yeah, what is this one equal to? This is the value at time 1 for getting $1 at time 1. How much are you willing to get to pay for $1 immediately? Very good, now. This is 1. And what about the first one? This here is the value at time 0 for getting $1 at time 1. right? And our model is that I have a money market account. So I can buy and sell the money market account. If I put $1 into the money market account at time 0, it's going to grow to 1 plus R0 at time 1. So what would be the value? What would the value at time 0 for getting $1 at the end of at the next time point? And so the picture is, if you put $1 into S0 at time 0, you get 1 plus R0 at time 1. So how would you adjust it? How would you adjust this? So you would get you don't want to get 1 plus R at time 1. You want to get 1 here. So how would you adjust it? No, we don't get to choose R0. We don't get to choose R0. Right? R0, this is our model. R0, this is the stochastic interest rate. We don't know what that is. We do not get to play around with. What we get to play around with is, instead of investing $1 into S0, we should be careful because there's no little r. There's no little r. Yeah, Mao, you're right. So the value here is going to be 1 divided by 1 plus R0. And so what you do is you move around here. You move this thing around, and then you move this thing around. So now this becomes 1. So you invest that much at time 0, and then you get this thing at the end. So now let's move into the second one here. So we had played now with the first one. So now let's play with the second one. So I have a 2 now. So I have a 2 now. So let's start out with B2, 2. What should that be? 2 혹시 a zero coupon bond. What does it pay at the end? We always get $1 at the end, right? Not 2. You're only going to get 1, right? This thing here should be 1. Okay. So then we go 1 up. B, 1, 2. What should that be? Yeah, we'll do the same analysis, right? If I put in $1 into S0 at time 1, you get 1 plus R1 at time 2. So what should we put in here? So do 1 over 1 plus R1. Very good. Don is right. And so what about this one? So here we do, so we put 1 into S0 at time 0. You get 1 plus R0 times 1 plus R1 at time 2. So we're suggesting that this is 1 over 1 plus R0 times 1 plus R1. Any objections? This here is no. This is not correct. This is not correct. So where's the problem? Let's have a look. What's on the left-hand side? This is the value. This is how much you have to pay at time 0 to get $1. To get $1. So how much you have to pay here to get $1 over here. What kind of measurability properties should that have? Should this be measurable with respect to, that should be measurable with respect to what? If I'm trading something at time 0, it should be measurable with respect to R0. This should we call it F0, Dawn? It should be F0 measurable. Right, because we're trading at it. Okay, so the left-hand side, this should be F0 measurable. And what do we have here? What is that measurable with respect to? What kind of measurability do I have of this one? This is F1. Okay, so this equality sign here is problematic because on the right-hand side, I'm F1 measurable, on the left-hand side, I'm F0 measurable. So this is a no. Here we're good, right? Because the left-hand side, this is F1 measurable, the right-hand side is F1 measurable. This here is F2 measurable, and this is also F2 measurable. So that's correct, Don. You cannot have R1 appearing over here. You cannot have R2 appearing here. You cannot have R3 appearing here. It won't work. So it doesn't work this easily. We cannot just create zero coupon bonds by looking at these ratios the way that we're doing here. It will not work. Something else needs to happen here for this to work. And this is really what fixed income is all about. Building these zero coupon bond models. This here is not going to do it. So I think this is a good place to call it quits today. I just want to remind everybody that we have there's a problem session tomorrow, and then on Thursday and Friday mornings we're going to have office hours as we usually do. Are there any questions before we say goodbye? So next time we're going to continue with fixed income. What is B01? Well, B01 is B01. This is the what are you willing to pay at time 0 to get $1 at time 1? Right, n here is equal to, in the chat question, n is equal to 0, m is equal to 1. Right, so it's a zero coupon bonds price at time 0 when it expires at time 1. Other questions? Are there other questions or comments? So next time we're going to try to figure out what to write here on the right hand side. So this is just showing us that we cannot write what we have here. This is not going to work. We need to write something else here, and so that's where we're going to start out next time. Okay, I will see you guys hopefully during office hours, and otherwise I will I'll see you guys next Tuesday. Yeah, Dawn, I mean, this is a big part of what we end up writing on the right hand side. This is a lot more involved than just what we have here. Right? So this is just to show you that the naive thing that one might want to try to do is not going to work. Okay. Welcome, guys.